All of the theories we're going to look at in this section, though, basically want to answer the same thing, and that's how do you go from atomic orbitals into molecular orbitals, or the orbitals of molecules? And it's kind of a more interesting question than you might think. Like, why do the figure 8 p orbitals, which are shown in the upper left-hand corner there, or the spherical s orbitals, which is that big blue thing there, how do you turn at best 90-degree angles into the 109-degree angles that Vesper geometry predicts so well? So the question really is, how do you go from these atomic orbitals to the orbitals that are in molecules? And both theories, both of the main theories we're going to talk about, attempt to answer this question in their own way. So the two main theories of bonding which are used in chemistry, the first one's called valence bond theory. Valence bond, or VB theory, was first proposed by Linus Pauling, who was actually one of the great Oregon chemists. Pauling went to Oregon State University before going on to get his PhD and lots of stuff. He's a fascinating person. But anyway, Linus Pauling in the valence bond theory basically proposed that the valence electrons, those outer electrons on atoms, are localized between atoms, or they can be lone pairs for that matter. And each bond that forms is basically one electron from each atom. Those electrons overlap, and they form then bonds that are stabilized by two nuclei. And valence bond is really great for normal kind of operations, which is cool. We'll talk about that. But the other theory, which is a newer theory, is called molecular orbital theory, or MO theory. And Mulliken there was the person that first kind of got this ball rolling. And basically, in molecular orbital theory, he also was talking about valence electrons, but the valence electrons are delocalized over the entire molecule into what he referred to as molecular orbitals. And we will draw in this section some of those molecular orbitals, which are seen right there. At first, it might look a little bit strange. I completely understand, but we're going to make sense of all of this. So hang tight while we talk about valence bond theory first, and then we'll talk about molecular orbital theory. Now, a sigma bond, or a single bond, is one of the bonds we talked about when we draw Lewis structures. And you can think about a sigma bond as basically having two atoms that overlap. And then they overlap in just the right amount, you actually make a pretty strong bond. So on the far right there are two atoms at quite a distance away, and there's no overlap, there's no interaction. And as the atoms get closer, i.e. as you go right to left, first you have a partial bond, like some overlap and some attraction, but then you get to some kind of ideal place where you have the maximum attraction. And that's what this part here shows on the picture. That shows the ideal spot where you have the maximum attraction. However, if you start getting too close to each other, then the protons start repelling the other protons, and the electrons can't help but start repelling the other electrons. So there will be places where it gets too close. So you want to have like the Goldilocks effect, all right? Not too close, but not too far, just some kind of ideal part. And when we'll talk about energy in a future chapter, the energy of the bond can be predicted, and so can the bond length, which is really cool. So this is the interaction between two 1s orbitals to make hydrogen, H2. And again, it forms this sigma bond. So sigma bond you can literally think about as the orbitals getting close enough to interact. There are other kinds of sigma bonds besides s orbitals coming together. So the top represents the two 1s orbitals of two hydrogen atoms to make the H2 sigma bond. And you can see they get close enough, they start to stick together, and that's what makes the bond. It's kind of like if you have a handshake, all right? You want to have an ideal length between the two people. You don't want to get too close into the personal space, but if you're too far away, the hands can't make contact. It's kind of a silly analogy, but it does work. But that example uses two 1s orbitals. And in chemistry, we've definitely seen where 2p or even 3p or higher orbitals can come together. So the second example there is where hydrogen's 1s orbital connects to a fluorine's 2p orbital. Now, one of the orbitals on fluorine has a single electron. If you remember from the electron configurations, fluorine is 1s2, 2s2, 2p5. And that 2p5, those 5 electrons are distributed over 3 orbitals. You can have 2 electrons per orbital. So what that means is one of the orbitals has only a single electron, and that is the orbital that's going to bond with the hydrogen. And like before, the orbitals have to get close enough so they bond to make the sigma bond, no problem. But you could also have, in the last example, two 2p orbitals, or two 3p, or 4p, etc., etc. And when they come together and get close enough, they start to interact. There becomes an ideal distance between them. So sigma bonds can form between any kind of atomic orbitals.